Imagine a bouncer, right? A bouncer at an incredibly exclusive, super high-stakes VIP club.
Okay, I'm picturing it.
But this particular bouncer suffers from, like, severe cartoonish short-term memory loss.
Oh, that sounds like a terrible bouncer.
Yeah, totally useless. So you walk up, you show your ID, and he lets you in. Great. But a few minutes later, you step out to the patio for some fresh air. When you try to walk back inside, he stops you and demands your ID all over again.
He's never seen you before.
Exactly. You head to the bar, ID check. You walk toward the restrooms, ID check. Every single time you make a move, he treats you like a complete stranger.
That would be exhausting. I mean, nobody would stay at that club.
Right. But that exhausting, highly inefficient scenario, that is exactly how early internet security worked back during the dot-com boom.
It really was the Wild West back then.
It was. And welcome, everyone, to the WeCyberYou Unlocked podcast.
It's great to be here.
Before we unpack that bizarre reality, take a quick second to hit that follow button on whatever app you are using right now.
Yeah, please do.
And if you find yourself wanting more after we wrap up today, make sure you head over to WeCyberYou.com for a ton of extra content just like this.
Tons of good stuff on there.
So today's deep dive is built on this really fascinating stack of notes we got titled The Architecture and Logic of Stateful Inspection Firewalls.
Which sounds super dense, but it's actually fascinating.
Yeah, our mission today is to give you, the listener, a shortcut to understanding these invisible digital bouncers that protect our modern networks.
Right, because we want to explore not just what they are, but, how they actually think.
How they manage memory, why they're so foundational today, all of it.
Exactly. And to fully grasp why stateful inspection was such a monumental shift, we really have to look at the nightmare it replaced.
The bouncer with amnesia.
Yeah, the amnesiac bouncer.
Yeah.
In those early .com days you mentioned, networks relied on basic packet filtering. We call those stateless firewall.
Stateless, meaning no state, no memory.
Right. Under that model, the firewall treated every single piece of data, every packet, as a completely isolated event in a vacuum.
Wow.
It had absolutely zero memory. It didn't know if a packet was part of an ongoing legitimate conversation or just like some random data showing up out of nowhere.
Okay, let's unpack this. Because for anyone who actually remembers managing networks back then, stateless firewalls were just an administrative disaster.
Oh, an absolute nightmare.
Right. If the firewall evaluates every single packet against this massive master list of rules, that means administrators had to manually write access control lists for every conceivable direction of traffic.
Every single one, top to bottom.
You had to explicitly say, allow my user to reach out to the server. And then write a completely separate rule saying, allow the server to talk back to my user.
Yeah, the return traffic wasn't guaranteed.
Which is wild. If you had thousands of users doing thousands of things, that rulebook just became bloated, unmanageable, and incredibly slow.
You hit the nail on the head. I mean, it wasn't just a management nightmare. It was a massive performance bottleneck.
Because it's reading the whole book every time.
Yeah. The hardware had to read from top to bottom through thousands of rules for every single micro interaction. So the big shift happened when the industry introduced this stateful inspection firewall. This added one distinct superpower to our digital bouncer.
Which is the awareness of connection state.
Right. Awareness.
Meaning it finally acquired the ability to remember you. It understands context.
Exactly. It realized that network communication is not just a flurry of disconnected data points.
Right. It's a flow.
Yeah. When your computer talks to a web server, it is engaging in a continuous logical conversation.
Okay.
A stateful firewall tracks the state of that network connection over its entire lifespan.
So it's asking context questions now.
Very critical ones, like where did this communication start? Or is this packet part of a session I already approved?
Does this traffic actually make sense right now?
Exactly. Does it make sense in the context of our ongoing conversation?
Which brings us to the actual mechanics of it, because I'm wondering, how does it store that memory?
That's the big question.
Right. If a corporate firewall is processing, I don't know, millions of concurrent connections, it has to be keeping an insanely fast, highly organized ledger somewhere.
It does, and that ledger is the absolute brain of the firewall. It's called the state table.
The state table, or sometimes I've seen it called the connection table.
Yeah, connection table is the same thing. Physically, this is a highly dynamic database held entirely in the firewall's RAM.
Okay, it's short-term memory.
Right, which allows for incredibly fast read and write speeds. It uses advanced data structures, often hash tables, so it can look up a connection in literal microseconds.
So what exactly is it writing down in this hash table?
A lot of very specific coordinates.
Because if we're talking strictly about the network and transport layers here, like the raw plumbing of the internet, what are the identifiers it logs to prove I am who I say I am?
Well, it tracks a very strict set of rules. First, it logs the source IP address.
The exact origin of the traffic.
Right. And then the destination IP address.
Yeah.
Then it tracks the source and destination ports.
Oh, the ports are crucial, right?
Very.
Yeah.
Because they identify which specific applications or services are actually talking.
Got it. What else?
It logs the protocol being used.
Yeah.
And it also monitors session timers, the direction of the flow, and sequence validation numbers.
Wait, I need to challenge the efficiency of this for a second.
Go for it.
Because if it is dynamically logging all of those variables, the IPs, the ports, the specific transport protocols, the countdown timers, and writing that to memory for millions of concurrent connections,
Yeah.
doesn't that just create a totally new bottleneck?
It sounds like it would, right?
Yeah, it sounds like we just traded the inefficiency of checking everyone's ID for the inefficiency of writing a massive novel about every single person currently inside the club.
I get why you'd think that. It sounds totally counterintuitive, but it actually drastically improves performance.
How? Writing to RAM takes resources.
It does, but the upfront cost of writing that entry into RAM pays off immediately because of how it handles the subsequent traffic.
Oh, I see.
To really see why, we need to look at the actual mechanics of a TCP handshake.
Okay, the three-way handshake.
Right. It isn't just a simple hello. It is a highly structured puzzle.
Right, because TCP transmission control protocol is connection-oriented.
Exactly.
It requires both sides to agree to talk before any real data is sent.
Correct. So let's say your laptop wants to load a web page.
Uh-huh.
Your machine sends out a very specific initialization packet, a TCP SYN packet.
SYN standing for synchronize.
Right. Your computer is essentially saying, I want to start a conversation, and here is my starting sequence number.
And the firewall catches this packet?
Yes. Because this is the very first packet of a new session, the firewall checks your master security policy. It asks, are you allowed to talk to this server?
Let's assume I am. So the firewall looks at the rules, gives me the green light, and allocates a tiny block of its RAM to create a new entry in the state table.
Right. And it marks your connection state as starting.
Okay, so the packet passes through to the web server. The web server receives my synchronize request and replies with a SYN ACK packet.
Synchronize and acknowledge.
Right. It is saying, I acknowledge your sequence number, and here is my sequence number to prove I am really here.
Perfect. Now, when that reply hits the firewall does not check the massive rulebook.
It just checks the state table.
Exactly. It verifies that this server's response perfectly matches the session you just initiated.
And if the math checks out?
The firewall updates your state table entry to established.
Ah, I see. And once that session is marked established, the firewall stops acting like a rigorous investigator.
Right, it relaxes a bit.
For the rest of the conversation, as data flows back and forth, the firewall just glances at the state table.
It just checks the tags, basically.
If the packet belongs to an established, valid session, it is automatically waved through. It gets to use the fast lane.
That is the magic of it. You pay a tiny processing tax up front to create the state entry. But the remaining 99% of the packets in that session bypass the heavy security policy checks entirely.
That is incredibly efficient.
It is. And when the conversation ends, one side sends a finish packet, a finish flag, or an RST, a reset packet.
The formal goodbye.
Right. The firewall sees that goodbye, scrubs your entry from the RAM, and frees up that memory block for the next user.
But wait, what if someone just unplugged their computer and never sends that formal goodbye?
Ah, the ghosting scenario.
Yeah, did they just take up memory forever? That is where the session timers come in, right?
Exactly right. The firewall just counts down, and if it hears nothing for, say, an hour, it clears the table.
Okay, that makes sense. It prevents the memory from filling up with dead connections.
Precisely. I mean, exactly. It keeps everything clean.
Let's move from the abstract hardware mechanics to how this actually protects you in your day-to-day life.
Good idea. Let's make it practical.
Let's look at a scenario based on the sources we're doing this deep dive on. You open up your browser and type in https.bank.com.
A very common scenario.
Right. Your browser initiates the TCP connection. The firewall checks the rules, sees outbound web traffic is allowed, and writes your session into the state table. Your request goes out to the bank.
Now think about the bank's response.
Okay.
The bank's server processes your request and sends the encrypted web page data back to your IP address.
Right.
Under the old stateless model, a network admin would have to leave a permanent hole in the firewall, like a static inbound rule, allowing traffic from the bank's IP address to enter your network.
Which is incredibly dangerous.
Oh, hugely dangerous.
Because if you leave a permanent hole open for bank.com, what happens if the bank server gets compromised?
You're completely exposed. But with stateful inspection, the firewall remembers your outbound request.
Right. It natively understands that the return traffic from the bank is just the second half of a conversation you already started.
Exactly. It temporarily opens a dynamic pinhole just for that specific traffic.
And the moment the session ends, the pinhole closes.
Bam. Shut tight. No permanent inbound rules required.
Here's where it gets really interesting, though. Let's talk about malicious actors.
The hackers.
Yeah. Let's say a hacker is scanning the internet. They want to attack your device. They know you probably use bank.com, so they spoof the bank's IP address.
A classic move.
They forge the network headers so the packets look exactly like they are coming from the bank's legitimate server, and they fire those packets at your network.
If you were using a stateless firewall with a permanent inbound rule for the bank, those spoofed packets would bypass the perimeter entirely.
Oh, wow.
Yeah, the firewall would look at the forged return address, say, looks like the bank to me, and let the attack right through.
But the state table completely neutralizes this.
It does, because when those spoof packets hit a stateful firewall, the firewall immediately checks its memory.
It looks at the ledger.
Exactly. It says, I have no record of my internal user asking for this specific data.
Right. There is no established TCP handshake in my state table that matches these sequence numbers.
Yes. Because the traffic lacks context,
Yeah.
the firewall doesn't even bother checking the main rulebook. It drops the packets instantly.
So synthesizing all of this, stateful inspection provides massive security by demanding context.
Context is everything.
Right. It drastically reduces administrative overhead by handling return traffic dynamically.
Yep.
And it stops spoofing attacks dead in their tracks because an attacker cannot inject packets without successfully faking a complex, multi-step mathematical handshake that the firewall is actively monitoring.
That is a perfect summary of its power.
Okay, but let's pivot for a second.
Right.
Because if stateful firewalls are this smart, if they perfectly track conversations and dynamically block unrequested traffic,
I know where you're going with this.
why are cyber attacks still happening every single day?
It's a fair question.
Right. Why do major corporations with top-tier firewalls still suffer massive data breaches? These things clearly have blind spots.
They absolutely do. Stateful inspection was a massive leap forward, but it operates under some very specific, rigid limitations.
Let's break those down. The sources mention application blindness.
Yes.
If I am reading this right, if the firewall is only verifying the IP addresses, the ports, and the TCP sequence numbers, it isn't actually looking at the data being transmitted.
Not at all.
Let's use a modern metaphor. This sounds exactly like a shipping container inspector at a port.
Oh, I like where you're going with this.
So the inspector checks the exterior of the shipping container. They verify let's say it claims to be textiles from Rotterdam.
Okay.
They check the weight, they verify the padlock is intact, and they confirm the destination warehouse. Everything on the outside looks perfectly legitimate.
So they stamp the paperwork and wave the truck through.
Exactly. But the inspector never actually x-rays the container. They never open the doors.
Right.
They have no idea that hidden inside those textiles is a crate of smuggled contraband.
That is a brilliant analogy, much better than the old envelope metaphor people used to use.
Thanks.
You're describing exactly how Layer 3 and Layer 4 inspection works.
Network and transport layers?
Right. The network layer and the transport layer are just the shipping container and the manifest. The firewall is a master at verifying the exterior.
But it can't see inside.
Exactly. It has absolutely zero understanding of Layer 7, the application layer. It cannot comprehend web application logic, API calls, or user intent.
So if a hacker sets up a totally legitimate-looking TCP handshake, the firewall allocates the state table entry. The connection is marked established.
Yep.
But then the hacker sends an HTTP request containing a malicious payload like a SQL injection designed to trick a back-end database into dumping all its user passwords.
The stateful firewall waves it right through.
Wow.
Yeah. To the state table, the shipping container is flawless, the sequence numbers align, the IP is valid, the session is active.
But it's full of contraband.
Exactly. The firewall simply lacks the capability to deeply inspect the payload, unpack the HTTP headers, and realize that the actual database query inside the container is a weapon.
That is a massive architectural blind spot.
It is. But that isn't the only vulnerability.
Really?
Yeah, the very mechanism that makes stateful inspection so fast, its memory, is also its biggest physical weakness.
Oh, because memory is finite.
Right. Maintaining that dynamic state table requires hardware resources.
Yeah.
Every single concurrent connection consumes a tiny fraction of the firewall's RAM and CPU processing power.
Which means there is a hard mathematical limit to how many conversations a firewall can track at one time?
Exactly. And attackers are incredibly adept at weaponizing that physical limit. This brings us to a devastating technique called state table exhaustion.
Or more commonly known as a SYN flood attack.
Yes, the SYN flood.
Let's figure out how this works based on what we discussed.
Okay, walk me through it.
If the firewall allocates memory the moment it sees a hello packet. Wait, if a botnet sends millions of SYN packets, millions of hellos, the firewall has to allocate a tiny block of memory for every single one of them, right? It puts them in a half-open state, waiting for the server to reply. What if the attacker just never replies? Does the firewall just hold that memory open?
You just deduced the exact mechanics of a SYN flood.
Seriously?
Yeah. When the firewall receives a SYN packet, it sets up the state table entry and starts a timer, maybe 30 or 60 seconds, waiting for the rest of the handshake to complete.
And it holds that memory buffer open the whole time.
Right. Now imagine a coordinated botnet firing millions of forged SYN packets from random fake IP addresses into your network every single second.
Oh, man. The firewall dutifully creates millions of half-open entries.
Yeah.
It is allocating RAM for conversations that are never going to happen.
And very quickly, sometimes in a matter of seconds, the hash table completely fills up. The firewall exhausts all of its available RAM.
It's like a coordinated mob rushing that bouncer at the club we talked about earlier.
Exactly.
They hand him thousands of fake IDs and then just sprint away.
Leaving him totally overwhelmed.
Right. The bouncer's just standing there holding all these IDs, desperately trying to log them into a system. When a real, legitimate VIP walks up to the door, the bouncer physically cannot process them.
That is exactly what happens. Once the state table is full, the firewall goes into survival mode.
What does that mean?
It starts dropping all new packets because it literally has nowhere to write the connection data.
Wow.
Legitimate users are completely blocked from accessing the network.
Yeah.
The existing connections might stay alive, but no new traffic can enter.
So it's a highly effective resource exhaustion denial of service attack.
Highly effective.
So given these severe limitations, the total blindness to application layer attacks like SQL injections, and the structural vulnerability to having its memory flooded, I think it's completely fair to wonder, is this technology outdated?
I get asked that a lot.
Right. Should we be moving away from stateful firewalls entirely?
It is a logical question, but the answer is a definitive no.
Really?
Yeah. Stateful inspection is not a relic of the past. It remains the foundational backbone of almost every enterprise perimeter defense, data center appliance, and cloud security gateway operating right now.
So what does this all mean? If it has these glaring flaws, but we still rely on it, how are we actually securing modern infrastructure?
The key is that modern security does not replace stateful inspection. It builds directly on top of it.
Okay, layering.
Exactly. Think of the state table as the chassis of a high-performance vehicle. You cannot build the car without it. It provides the essential structure.
Right.
But you also wouldn't drive just a bare chassis on the highway without adding airbags, seat belts, and a collision warning system.
That makes sense. So what do those advanced safety features look like in a modern network stack?
They look like next-generation firewalls, or NGFWs.
Ah, I've heard of those.
Right. An NGFW takes the core memory and lightning-fast efficiency of a state table, but it adds deep application awareness and intrusion prevention systems.
Okay, so going back to our container analogy.
Right. It checks the shipping container's manifest, but then it actually opens the doors, x-rays the cargo, and looks for malicious payloads.
It solves the application blindness problem.
Exactly.
And we also see web application firewalls, or WFs, doing something similar.
Yes, WFs are crucial.
They sit specifically in front of web servers, using state awareness combined with intense scrutiny of HTTP traffic to catch those SQL injections and cross-site scripting attacks that the basic firewall misses.
Exactly. The stateful firewall acts as the initial high-speed filter. It handles the massive volume of internet noise, quickly dropping the obvious spoofed packets and invalid connections.
Right.
By doing that heavy lifting, it frees up the CPU-intensive tools like the WAF or the NGFW payload inspectors to focus their processing power strictly on valid, established conversations.
It is all about a layered defense, but I want to push on this a bit, especially regarding modern architectural shifts.
Okay, push away.
We hear constantly about zero trust architecture.
The buzzword of the decade.
Totally. The core philosophy of zero trust is never trust, always verify. It assumes that the network is already breached.
Right.
But doesn't that directly conflict with the logic of a stateful firewall, which inherently trusts a connection once the state is marked established?
That is a phenomenal point, and it is a major debate in network engineering right now.
Really?
Oh, yeah. On the surface, they do seem philosophically opposed. Stateful inspection says, you completed the handshake, you are on the list, you are good to go.
And zero trust says, I don't care if you are on the list. Prove who you are again before you touch this specific database.
Right.
So how do they coexist?
They coexist because zero trust still requires session tracking to function efficiently.
Oh, interesting.
Yeah, in a zero trust model, you are continually validating identity and device health. But you cannot do continuous validation if you don't have a reliable way to map individual packets to an overarching session.
And the state table provides that mapping.
Exactly. Zero trust essentially takes the stateful concept and elevates it from the network layer to the identity layer.
Okay.
It uses the state table to maintain the connection, but it constantly reevaluates the authorization criteria over the life of that connection.
That makes perfect sense. The state table is just the underlying physics engine that allows the higher level zero trust logic to operate.
Exactly. Without stateful tracking, implementing continuous verification would require authenticating every single individual packet.
Which would bring any network to an absolute crawl.
It would be completely unusable.
This has been an incredibly clarifying journey. To quickly recap what we covered today in this deep dive, we explored how stateful inspection revolutionized network security by moving us past the dark ages of mindless, isolated packet filtering.
Right, giving the firewall a memory.
Exactly. It introduced memory and context. It understands that network communication is a continuous conversation, allowing it to efficiently track sessions, automatically handle complex return traffic, and inherently block spoofed packets.
That's a massive upgrade.
And despite its vulnerabilities to things like application blindness and memory exhaustion, it remains the indispensable chassis that all modern security tools, from next-gen firewalls to zero-trust frameworks, are built upon.
It truly is a masterclass in how adding a little bit of structural memory can completely transform the capabilities of a system.
Definitely.
But as we wrap up, I want to leave you with a lingering thought.
Oh, I love these. Let's hear it.
We talked a lot about TCP, the protocol that requires a formal handshake and a formal goodbye.
Right, a structured conversation with a clear beginning, middle, and end.
But the internet is changing rapidly. We are seeing a massive surge in connectionless protocols like UDP and modern implementations like QUIC, which are heavily used for streaming and gaming.
Okay.
These protocols do not have formal handshakes. They just fire data at a destination.
Wow.
Furthermore, we are seeing AI-driven traffic patterns and decentralized web architectures where the very definition of a session is constantly shape-shifting.
So the old rules don't apply.
Right. If the future of communication abandons the structured, predictable conversation, how will our digital bouncers adapt?
Ooh, that's a good question.
How do you track the state of something that refuses to follow the rules of a traditional conversation?
That is an incredible question to leave on. The nature of the digital conversation is fundamentally changing, and our defensive architecture will have to evolve right alongside it to keep up.
It's going to be a wild ride.
Thank you so much for joining us on this deep dive. We hope it gave you a completely new perspective on the invisible architecture keeping your daily digital life secure.
Thanks for listening, everyone.
Remember to visit WeCyberYou.com for more insights, articles, and resources to help you stay ahead of the curve. Until next time, stay curious and keep learning.